Thank you for coming and for continuous process of joining with more and more people joining. So this is a course in computational chemistry, and the goal of the course is to enable computational characterization of molecules and materials for science, physics, chemistry, and engineering. Maybe this year no one is concentrated on biology, but in principle I can add coding to the aspect of the class. And the outline of the course is 4 chapters. So first chapters are background in theory and molecular modeling in labs. So in next week on Thursday there will be presentations where each of class attendees will present one of the practical skills. There was a sign up list. In this sign up list we already have a lot of volunteers, and I will help with encouragement to bring your attention to someone who wants to take this one and this one, because it is already covered in the labs. And here one can show like how to install MobiX, how to create directories with something simple. And when we meet next time, we'll cover this theme and more, and we'll try to spread all this load equally on everyone in the class. So maybe someone will do 2 and 1.5. There is one active homework to build a model, and there is no hard deadline. If you already completed this, send an email as a printout. You can keep doing it during the lab and submit it later. And when we meet on Thursday, I will design a little homework to entertain you next weekend. It will be basically a summary of equations that we are going over. So it will be also something that I can do in 5 minutes. Do not focus right now. I will go over next time. Yes?
Yeah, for that, how many users do you think is a quick demo about the specific?
Exactly. We will try to fit how many, like 8 people into 1 hour, which means like 5-minute presentations and 1 minute per question, which means like 3, 4, 5 slides, no more. If you sum of class attendees, and I remember myself also on the other side of their first impression is like, oh, I need to present something, how hard it is, I cannot start. And then after you start talking, everyone goes over the limit. And I need to stop and kick from the stage. So it's human nature. As soon as you stop here, you come here, you try to use more time than the original assignment. So before we go to the slides, let's chat a little bit in the informal way where we are, where are we going. So we do want to predict properties of materials with computational models. We build models like a set of nuclei and assume that electrons flying nearby, and there are interactions between nucleus, between electrons, and nucleus to electrons. We put them into an and we do want to take into account quantum nature of all these particles, electrons and nuclei. And then we are coming to the idea of molecular hereditary equation, where positions of all electrons and nuclei are independent variables of a wave function, which are wave function of 1,000 variables, which is a little discomfortable. And the pure rigorous formulation of a problem and course would stop at this point if we would have unlimited computational power. But since resources are limited, we need to divide and conquer as ancient Romans and simplify the problem. And the first step is to split electronic and nuclear derivative. We represent wave function of a molecule as a product of electronic wave function and nuclear wave function. And we are going on along this way. So it's laborious. So on the meeting number 2, and do not worry, I will repeat the same things with slides again. So on the meeting number 2, we did select favorite terms in the molecular Hamiltonian, pulled it out, and thought those are terms in the Hamiltonian responsible for the electronic degree of freedom. We can use it as a temporarily electronic Hamiltonian, find its eigenstates, which will dictate properties of the molecule for fixed nucleons. And then the solution of this wave functions of electronic states can serve as basis to find overall wave function of a molecule, assuming that ions can take any position. Solving this electronic wave function for each position in place, and then finding this nuclear wave function. Good plan. But some of you are already very experienced in molecular dynamics and you know the beauty of it. So if we forget about all quantum properties and just consider each nuclei as a point charge, or just run something like Newtonian motions along potentials. These are a way to get back to this comfortable arrangement with all background of theories and abstract concepts. Yes, it is possible, but we need to neglect some processes, some interactions, and we need to clearly determine what we are neglecting. So the key terms that are being neglected on the way of splitting electronic and nuclear freedom and leaving behind quantum properties of nucleus are so-called non-adiabatic couplings. So it is a new term that we will define today. They are mentioned in this little handout, and typically these non-adiabatic couplings are coming in bundle with the concept of potential energy surface. So although they should come bundled, we will focus more on defining non-adiabatic couplings today, and we will focus more on definition of potential energy surface when we meet next time on Thursday for the lecture. Any protests? This gentleman or against moving coach. So we are getting background in theory, skills, and later communications. So the computational chemistry is running right software on the right hardware with the right theories. And here are the summary of basic quantum theory. it's just a summary of what we did in previous units. Then we set up positions of each ion, each electron, set up distances and momentum between them, and set up Hamiltonian, which includes kinetic energy of nuclear electron and then introduction nuclear electron. And then we identify part that deals with electrons and declare that solution of this part, the electronic wave function that depend on positions of electrons over it as argument and on nailed down positions of nucleus as parameters will be a good basis of overall molecular wave function. And this unknown coefficients also play a role for nuclear wave functions. By the end of today's meeting, we are going to get an equation for this nuclear wave functions. And we will declare what is being neglected in order to write down the wave function in the form of product to become. So, on the way of solving this problem, and feel free to raise back and correct. There is nothing new right now. I'm just reviewing what we did previous meetings. So we are taking overall molecular shading regulation with kinetic energy of nucleus, potential energy of nucleus, and all terms that relate to electrons. So Hamiltonian acts on wave function equals eigen value. Then we plug in instead of wave function a product of electronic and nuclear terms. And then we are trying to remove, to omit, to extract and put behind electronic wave functions which are denoted as letter phi. If we believe in quantum field, if we assume that our electronic wave functions are good functions, then they must obey first normality. Right? It's not here, right? And then in this green font, we do have electronic wave functions coming up in the first power once each time. But if you would make it to appear twice, and if you would add an integration, as we see here in the red form, then there is a chance to practice the property of orthogonality and completely remove electronic wave function. Pairs of electronic wave functions will be replaced either by 0 or by 1, and we will stay only with nuclear wave function. And then get a shared equation for nuclear wave function, which means a distribution of where each nuclei is a certain probability. By practicing this orthogonality, we experience simplicity and complexity. Simplicity for lower 3 lines, and a little challenge when we deal with the upper line. The challenge originates from the commutation properties, so that operators and wave functions are not allowed to swap the order of it. One needs to be very careful, and if one swaps the order, if one wants to multiply it on the left, and then put it right here, swap the order in the product with wave function, kinetic energy operator, and the function, one needs to pay a price. Or maybe it's not possible to swap. And by doing this, one may come back into the literal definition of this kinetic energy operator, which is called squared is derivative over position in place, then one needs to be careful to take this derivative. I'm done and I'm tired of already. So about now we will start something new. So very soon. So if we carefully practice orthogonality, and I think I'm not showing it this time, but you remember snake and mouse. The summation is like snake, and delta function is like mouse. And when they meet each other, they disappear. So, right, the lower three lines, we do not have 5 orthogonal functions anymore, and we do not have summation. But the index from A became B, right? Cause snake A mouse. But for the upper term, this trick cannot be done at once. One needs to process this expression here. And basically, I was trying to do it in the last minute of last meeting, but it was too much information. I decided to dedicate the whole lecture. Basically, we will look at this T capital and carefully apply second derivative to the product of these two functions. Let's move forward. And this slide will be desired outcome of this meeting. So after we do everything, in addition to Schrödinger equation for everything part, we will get Schrödinger equation for nuclear part. But something is being neglected here. So in more than half, majority of text in computational chemistry simply postulate that molecular wave function is a product of the nuclear part due to Born-Oppenheimer approximation. But by making this bypass and shortcut, we are missing an important part, and we are disabling an opportunity to describe such processes like combustion, explosion, formation of plasma. So if there are situations when this Born-Oppenheimer separation doesn't work, and it's better if we define it and carefully. In the text, it is not called computational chemistry, but like a third of the book is computational chemistry. He lives in Berlin, and it's not a small city, but there is a chance to run into each other instance. Right? And he was in my that's how I got known about it. So last year I was trying to invite everyone from the class 1 by 1 to take derivative. Maybe next year. Just don't have energy. Maybe some of you don't feel comfortable on one hand. On another one, I do not question your ability to take derivatives. You are already have. So we are taking second derivative over R capital, and for simplicity, I remove the index for so many ions, and I remove the vector because the terms and the arrangement will be repeated if we do this derivative. So it's second derivative over the position of the electronic function And this is the way how we probably take the derivatives for product of the first and second change from the product of the second and the first change. And then you take the derivative once again and then form one term under the material that be four terms. Right? Second, first. Right? Are there any terms which makes you combine together? Yeah. The same thing we just use as partial rule. So V terms. Let me invite you to think what are those terms and how to interpret them. Which of them is the simplest one in philosophical sense? Who votes that the first terms is simple? Who votes that the second term is simple? Okay. Who votes that the third is simplest? Who doesn't care? So I think it was equal amount of votes. Why should what does it? The question was not correct because it was not definition. What does it mean? I add my vote to the last one, and let's focus on this one. So the electronic wave function is unchanged, and derivative over position nucleus is applied twice to the nuclear wave function. How to interpret it? What does it mean? If we get what is needed. You would just energy of nuclei could be rated to wave function of nuclei, right? So just was what we defined. Second derivative of position of nuclei applied to nuclear wave function will give us kinetic energy of nuclei. And there is nothing else. No one interferes in this intimate life of these operators and this wave function. It's like hidden, closed, and perfect. Everything well defined. Kinetic energy of nuclear wave function. There is no admixture of electronic wave function stays just aside as a fact.
How it become kinetic?
Huh?
How it become kinetic?
What do you mean?
How? The kinetic term from the derivative. How I can? How you can say that this is kinetic term?
What is?
Like the form.
Yes. What is the form of momentum operator?
Yeah.
What is a form of? It's a question.
Peace kinetic term.
Huh?
Peace.
No. It's kinetic energy. So please, everyone, if you have notes or a piece of paper, write down an equation for momentum operator in quantum mechanics. For yourself, I'm not going to collect. Just write down as you. And let me bring your attention that there are two different things that we are discussing: kinetic energy operator and momentum operator. I'm asking not kinetic energy, but momentum.
P equals mg.
Write it down. Momentum of rate. Not yet. What is quantum theory? We can delay a little bit this class and just get back to basics. Like, what is a wave function? It's a thing that being squared gives a probability of a particle to be at a certain place, right? Known object. The globe is spherical, and electron is a wave. We all agree on this, basics. But then, in order to extract an observable from the wave function, what do we do with it? Like if the wave function of an electron or any particle is something distributed, and we need just one number.
Say it again.
If we need, like, all our instruments give numbers, like one number, like intensity of absorption at a given wavelength, one number. But for this number, all electrons are distributed in space contiguously. How do we extract a number from a function? When it's well, with functions one can do like integration, differentiation, right? Linear combinations, not many things. And there is a background, like axiom, postulate of quantum theory that for each observable in classical theory, there is a quantum analog that is represented in form of differential procedures, differential operators. So momentum is a derivative of wave function. Please raise or give me a little sign if it looks a little unusual or if you do not feel comfortable. I just want to see a feedback.
Yeah.
You show. You don't need to show it to everyone. You can show it to them. Momentum is a derivative of wave function. I see a little surprise on your face, which means you want some comments, right? I'm just looking at the slide that doesn't have vehicle. I think we were discussing it last time. So this would be lecture number 2 in quantum theory. An example of wave function. From your experience in other courses, even if you never took quantum theory, you have an intuitive vision of the orbitals, like in hydrogen atom, or maybe molecular orbitals in some mode, right? Like s, p, d orbitals. But if the electron is in the free space, like if there are no nucleus, only single electron, or if it is an electron in a solid, like a semiconductor, the wave function, which is of one electron as with independent variable position for takes the form of exponential. And, exponential has real and imaginary part, right? If this is R, then real oscillates like sine, imaginary oscillates like sine, and if you get it together, it will look like a spiral in the complex plane, right? This thing doesn't surprise you, I hope. So the R is position, the P, one needs to divide it by Planck constant. So my the P is how dense are these fringes, right? Please object or raise hands if you do not, if you protest. Like if you have sine P times x, the higher the frequency, the denser the fringes, right? The lower the frequency, the sparser the fringes. Okay. So the density of these fringes means how quickly the electron is moving inside this plane wave. So this construction is called plane wave, corresponding to electron moving forward in front direction. If it moves quickly, the fringes are dense. If it moves slowly, they're sparse. So we don't have time to go deeper, but there are some additional philosophical statements under this equation. And now we do have a little mathematical question. How to extract, if we start believing that this is momentum, how to extract this value P out of this function? Suppose that this function is not analytically, mathematically written down by equation, but it is a set of numbers in a computer. So we have just points in grid space. How do we extract this density of fringes? So if you take derivative over R of this huh? What is the answer? Huh?
I feel
So we have this normalization, I, P over H bar, and then we have the same wave function, H, right? So this part is wave function itself, and the stuff here is momentum, right? So what if we modify our operation slightly? If we tell if we show that h bar divided by I dr acting on the wave function, then this h bar and I will cancel, right? And we will get momentum times wave function. Okay? So therefore, every time, anytime we speak about momentum operator, we are replacing it by derivative over the position.
Can you please explain the last time again? About this.
Yes. Not a problem. You agree with second last line, right? Now I'm going to erase last line and rederive it once again. Now, instead of this DDR of phi, I plug in this thing, right? Because we showed what will be DDR over phi. Phi P H bar P with P H bar. Can we cancel something? So we can cancel H bar, we can cancel I, right? And the 1 over n e IPR H bar will be the function itself, right? Times phi. Good. Therefore, anytime we are speaking about P, we replace it by H bar over I times DDR. So this was an answer I wanted to see in your notes, right? So if you need to pass an exam on quantum theory, or if you need to, if you're going into space travel or on the inhabited island and you need only one equation that represents quantum theory that you need to engrave on your, like, on something. Like some people do have necklaces with motors if you are doing chemistry, but if you are doing physics, it is a good candidate. Yes?
So that was
Imaginary unit. So I will cover. So P equals H bar over I D R. So this is something that even if we plan to do agriculture or history, which has the basic fundamental of modern civilization. I
So R squared is -1.
yes. Square I is square root of -1. Okay, make sense? Like if you assume that we live like in ancient Egypt 5,000 years ago, and you can count only like fruits, maybe bricks to build pyramids, and then suddenly we have only nature of numbers, integers. But if we need to chop the harvest between like smaller number of people. We divide something. We add the procedure of division, and we come into rational numbers, fraction. Okay? And this was sufficient to live approximately up to 1,500. But then people started to try to make operation of square roots. And if the argument, and take the second order equations, x squared equals minus 1, what is the solution? And if we are within rational numbers, there is no answer. Okay? But if we assume that this operation is permitted, and we design a specific number, then everything becomes possible. And this is widely used in quantum theory. Good. Whew. Now you are certified experts in quantum mechanics. Everything else just follows out of this. What are we doing? Okay, we stop here. Right? Two derivatives means each of derivative means momentum. If you have two derivatives, it means momentum squared. And momentum squared means kinetic energy. I am just plain lazy and do not take care of the constants. But if one carefully pulls them, everything will be variable. With one constant computation of momentum, mass will be, if you start originally from kinetic energy, it will still be there. What is important that these differential operators are applied only to nuclear wave function. Therefore, this term out of all of them is called pure nuclear kinetic energy, because differential operator applies only to nuclear wave function. The rest are impure, dirty energy. So what does it mean? So here, operator of kinetic energy of nucleus is applied to electronic wave function. It's a little crazy. Electrons do not have positions of nucleus as independent variables. It's only the parametric. Okay? And electron wave functions are updating to change nuclear position so quickly that on a long time processes, this term typically drops. So it is not negligible only if you look on something on a very, very short time instant, comparable to the time of electronic rearrangement. This term, I wouldn't use the word dirty, I would tell mixing term. So this one, even more exotic. So it has kinetic, momentum operator applied to nuclear, momentum of nuclei applied to nuclear functions, time momentum of nuclei applied to electronic wave function. So this derivative is applied to each of them. So it's something very unusual and mixed, and it is very natural desire to drop these terms. And we will do it for like 20 lectures. Maybe we will return back at the very end of the course, but we need to know what we are neglecting. So these two terms are important if there are high energy, not in terms of nuclear bomb, but high energy in terms of like 2,000–3,000 Kelvin. If it is explosion, combustion, if one squeezes something or applies very intense laser field or intense electric field, so some exotic non-equilibrium conditions. Otherwise, in our regular life, liquid nitrogen temperature, room temperature, one typically drops these terms. Plasma reactions, breaking of molecules apart, strong laser, so it is electron transfer, so it is one this terms in. So once again, derivative applied of position of nuclei applied to nuclear functions is pure kinetic energy. And last, this other two terms are mixed. Born-Oppenheimer dictates us to neglect. So Born-Oppenheimer approximations means neglecting these terms. And then electronic and nuclear wave functions and Schrödinger equations become decoupled. The Born-Oppenheimer approximation works if nothing explodes, if nothing burns. So this one has yellow background because it's water. So we all are tired, exhausted with each soup. I need to go over some material so that we do not have leftovers towards next meeting. So here I'm not playing with it. I put back all constants, which I'm trying to avoid any time, but here. And if you look in your handouts, you will see something like this. So this equation corresponds to the top line in our molecular Schrödinger equation after we plug in solution form of product of electronic and nuclear equations. And after we multiply it from the left on the electronic wave function with different index and integrate. Here's one more thing that you may feel uncomfortable when we have Christ or and you already know that it will be delta function, right? There is a specific notation used broadly in physical chemistry, quantum theory, so-called Dirac notation. And such convolution is so it's called bracket notation. And this part of wave function is called bra. This is K, because of bracket. The coordinate, right? And right now we do not need it so much, but if you deal with spin, it's also a wave function, but it is a vector of only two components instead of a continuous function. And this bracket notation works equally well, continuous function and discrete. So integration is replaced by this bracket notation. I am developing the term of second derivative applied to alternative wave function. It's it will be too much, but you don't have time for it. So I'm skipping this one and focusing only on this first big stuff. So this one is a wait. I don't. So this is second derivative applied to alternative wave function. This is first. And here, derivative of position is applied to electronic. Here it is applied to nuclear. All these terms that we are going to neglect are can be denoted as theta AB, and what it does, it converts nuclear. It converts wave function A into wave function B. Right? We need to make a few steps more for making these definitions a little bit more readable and analyzable. Right now it's too many symbols. So where we see derivative, we can replace it by momentum if we take care of the constants. No. So the derivative of position of nuclei is replaced by momentum of nuclei. And later on, this non-adiabatic term can be simplified to the term with some constants. Then momentum of nuclei and matrix element of nuclear displacement between electronic wave functions. I know that we all are tired, including me. But and we will be able to forget it for 2 months. But by the end of the course, we will return to this. So, how to interpret this? Response of electronic wave function to change in position of nucleus. How much electronic wave functions are changed if you slightly move nucleus. So this response is multiplied by momentum of nuclei. So if nuclei are not moving, if it is absolute zero temperature, then this term is neglected because it's multiplied by momentum. If wave functions of electrons are not changing if you move nuclei, there is also no non-adiabatic term. So it needs.
Your call will be disconnected.
It's fine. We are still on the record, and it will disappear, but I will put it back. Don't worry. So if you slightly move, if there is a response of wave functions to change in position of nucleus, and if nuclei are moving, then this term is non-zero. So, last couple of steps. Delta function, pure nuclear wave function, pure kinetic energy of nucleus, nuclear wave function. Delta function here, there, and in here, instead of delta function, we have non-adiabatic couplings. Delta functions means matrix with ones along main diagonal and zeros everywhere, right? This one, at high temperatures, can be something different. But at low temperatures, it will be complete zeros, so we can neglect it completely. And if we remove this term, and if our snakes eat the mouse, so this summation and delta function disappear, then it will look as a Schrödinger equation for chi, for this nuclear wave function. Here. So we replace index A with index B, nuclear wave function, terms pure nuclear kinetic wave function in the nucleus, energy of nuclei to nuclear repulsion, an eigenstate of the ground state of electronic part if nuclei are nailed down at this specific distances. So it's contribution from electronic interaction. It's the only way of the consequences of existence of electrons. Times, all in brackets, times unknown nuclear wave functions equals eigenstate, which will be total energy of the molecule, equals this unknown wave function. Good. So in here, there is some leftovers, some imprint of electronic wave functions, but they are not coupled in a sense that we not jump between different electronic states. If one would keep the non-adiabatic terms, then motion of nuclei would promote jumps of electronic state between ground and excited states. These figures of potential energy surfaces and their discussion will be primary focus of our next meetings. So I'm giving a little heads up, but you can start relaxing. And important comment. So there is a dependence of electronic, of nuclear wave functions and energies on electronic Schrödinger equation, an electronic part. But there are no jumps. There are no transitions between electronic states. There are no thermally induced transitions between electronic states if we, at low temperature, if we neglect non-adiabatic coupling and accept Born-Oppenheimer approximation. Last thought. Schrödinger equation can be time independent, but it is a fraction. It is a simplified form. Generally, it is time dependent. If you do molecular dynamics, your ions are moving. If they're quantized, the wave functions of nuclei are moving. So time-dependent wave function of nuclei depend on time, and it looks a little bit different. So Hamiltonian here, Planck constant imaginary unit, time derivative here, right? And I think with this idea, it should be. Any other considerations should be left for next meeting. Thank you for questions. Meeting is done. Looking forward to see you Wednesday, 5 p.m. Tomorrow.
Hi, Dr.